The history of a particle moving along a line is a curve in a plane spanned by two axes representing the position and time. In the absence of interactions, the particle moves at constant velocity and its history is a straight line. The angle made by this line with a vertical direction is greater as the speed of the particle is greater. Observers moving at different velocities measure different speeds for other objects. To represent the movement of a particle in space, we need 4 dimensions, 1 for the time and 3 for the space coordinates x, y, and z. In this representation, there is an instance of the space at each time used to represent the position of the particle at that time. Each instance of the space is a slice in this 4-dimensional space. For simplicity, we will represent only 1 or 2 of the 3 space dimensions. For example, the movement of a spherical front wave of light at each time is a sphere, but in spacetime is represented as a cone. In relativity, space and time are inseparable parts of the 4-dimensional spacetime and not just successive instances of the space. Two observers moving with different velocities have different axes of time. Moreover, they slice differently the spacetime in instances of the space. Because of this, they perceive differently the distances and durations. However, in relativity, all observers agree that light moves with the same speed. The light cones define a new kind of perpendicularity between time axis and space slices, which is different from the usual notion of perpendicularity. The space slices measured by an observer are the slices perpendicular on her time axis. Because in relativity different observers have different time axes and space slices, when representing spacetime is more convenient to represent the directions of light, which are the same for all observers. Flat spacetime is infinite, but Penrose invented a way to represent it on a single sheet of paper so that the light directions are not changed. In these representations, the length and duration at different points are shrunk differently. The points which are at infinite distance are represented on the boundary of the diamond. It is enough to keep only the right side of the Penrose diagram because the left side is its mirror image. In general relativity, spacetime is curved. This has the advantage that the histories of particles moving under the influence of gravity are represented similarly to those which move freely by the straightest possible lines in the curved spacetime. In most cases, the curvature of spacetime is small, but it is strong enough to make the straight spacetime histories of particles appear as curved trajectories in space, precisely as the gravitational field would curve them. Gravity curves spacetime and bends the light cones. If gravity is too strong at some point, even light is trapped, the light cones are bent inwards and the black hole forms. The black hole is bounded by the surface which traps the light. According to the singularity theorems by Penrose and Hawking, inside the black hole a singularity appears. A singularity is a place where at least one of the following weird things happen. Distances between points in space which are not at infinity are infinite. Time intervals between moments which are not at infinity are infinite. Distances between distinct points are 0. Time intervals between distinct moments are 0. This can happen also because of a bad choice of coordinates, but in this case one can choose better coordinates in which no singularities appear. An example of singular coordinates is given by the polar coordinates of the plane. In polar coordinates, the points having the radial coordinates 0 and different angle coordinates appear to be distinct, yet the distance between them is 0. But a better choice of coordinates shows that these points in fact coincide and no such cases appear. So they are not true singularities, being due only to the coordinates. We can represent a curved spacetime containing a black hole which is neutral and doesn't rotate by a Penrose diagram, just like we do for the flat spacetime. The diagram looks similar to that of the flat spacetime, but there are two differences. The lengths and durations are distorted differently, and an object inside the black hole reaches the future boundary of spacetime after a finite time, although normally an infinite time is needed. That part of the boundary is the singularity. There matter just vanish, and together with it any information it contains and any secret it knows. In 1975, Hawking showed that black holes evaporate when quantum effects are taken into account. But if the information lost in the singularity never comes back after evaporation, quantum mechanics has a big problem. Therefore, many attempts to show that the information is not actually lost were made. Some hope that the Penrose theorem showing that inside black hole singularity always appear don't apply if quantum effects are considered. The most popular proposed solutions consider that the information is stored on a surface enclosing the black hole and it comes back during evaporation. But why shouldn't it be possible to resolve the problem where it actually appears, namely at the singularity? The main problem with the singularities is that the mathematics normally used for general relativity breaks down. Because the distances between distinct points in space either become infinite or zero, the geometric objects normally used to study curved spacetime become infinite or undefined. However, recently the geometric theory of spacetime was generalized to include singularities. This led to a geometric description named singular geometry, which uses finite and well-defined quantities which remain so even when distances between distinct points or time intervals between distinct times vanish. For such singularities, there are finite geometric descriptions. Moreover, the equations which previously gave infinite or undefined quantities now can be rewritten in terms of finite quantities only. For example, for the Big Bang singularity, the geometric objects but also the physical quantities used in the description remain finite. Initially, this method seemed not to apply to black holes because their equations also involved infinite time intervals and distances. However, it turned out that these infinities are due to the coordinates in which the black holes are described. The coordinates are singular, but if we replace them with non-singular coordinates, the only involved distances are finite or zero. Hence, the methods of singular geometry can be successfully applied to black hole singularities too. The spacetime containing a black hole which is neutral and doesn't rotate extends now naturally beyond the singular boundary to the future. The resulting Penrose diagram looks very similar to the one of a flat spacetime which doesn't destroy information. Moreover, the equations which previously gave infinite or undefined quantities now can be rewritten in terms of finite quantities only. Therefore, even if general relativity has singularities, they are not a big problem. The arguments that information is lost at singularities no longer hold. Black holes are not that good at keeping secrets.